model checking real-time systems, revisiting the alternating automaton route. This is joint work with my advisors, Srivatsan and Patricia. So model checking is basically there is a system, there is a specification. You need to check if the system satisfies the specification. Usual way to do so is you model the system as an automata, you model the specification, the knot of the specification as an automata, and then check the emptiness of the cross product. In real-time systems, like the system portion can be modeled using timed automata, and for specification, like we saw LTL and all in previous talks, but in real-time systems, we need to move beyond LTL in order to model properties. So we use something called MTL. So what is MTL? Metric temporal logic. It is like if you see the syntax, it is familiar enough to people who are familiar with LTL, but there is this interval that is added. So you can say things like the next action is an A occurring between time interval 2 to 3, and so on and so forth. So in 2007, it was proved that the MTL satisfiability for finite words is decidable, and how this proof was done was using a model called one-clock alternating timed automata. And so there was a construction given that is from the any MTL formula could be converted to an equivalent one-clock alternating timed automata formula, and then just checking the emptiness is enough to like decide the satisfiability. So this is the model we are going to use now, and I will go through all of this slowly. Firstly, what is one-clock alternating timed automata? It is timed automata, but now the transitions are formulas. So for example, here, if you see, so this is a ATA that models a property saying no two A's occur at time distance 1. So for people familiar with timed automata, you know that this is something that a timed automata cannot express. Like, no, it's not a timed regular language basically. But yeah, so for this, how it is modeled, okay. A good way to visualize alternating timed automata is as, say, obligation. So at each state, the formulas can be looked at as, okay, this is a new thread that checks something, and this is a thread that checks something else. So we can get like some level of simultaneous checking using just one clock. So here, like the Q0 state on an A goes to both Q0 and Q1 with a reset, which is like what this means. So I mentioned the MTL to 180 construction, which I will try and summarize a little, like consider it like a crash course on that, which is, so say this is the MTL formula. This is basically saying there is a subformula called true until A, and this formula should be satisfied until a point that you see C, and you have to see this C within the time like 1 to 2 time units. So how do you model this as an ATA? So each state can be looked at as the subformula to be checked. So like here you have the phi and you have this true until A subformula. For ease of like to make this picture a little bit clearer to understand, I'm also using this tick mark to show an obligation that has been fulfilled, which in the ATA semantics would go to true. Okay, so here this subformula can just be looked at as you're waiting for an A. The minute an A comes, this gets like the digits slowly. It goes. I mean, it loops on a B and C, and then the okay.
Can you share the screen overall?
Okay.
Just over there, just no. Yes. Full screen that first. Yeah, share.
Oh, sure. Yeah, I was here. So basically, on a C within 1 to 2 time units, you can just consider this obligation fulfilled and you can go to the true state. On an A, this subformula gets fulfilled, but you still need to check it for the, yeah, you still need to check it for the next instances. So you have a loop back to phi and you have a obligation fulfilled kind of transition. So hopefully there is like a little understanding of how ETAs look and how the MTL to 1ETA construction looks. So then what we saw was that 1ETAs are useful as a model because the emptiness problem there directly relates to satisfiability of MTL. Also, we saw that, okay, so there is a subclass of MTL called MITL that is studied a lot in terms of like satisfiability, but all of those satisfiability algorithms, they go directly towards timed automata instead of like so basically all MITLs are converted to network of timed automata and then timed automata algorithms are applied there instead of using 180s, even though there are algorithms that use 180s as like a intermediate step. So then 180s are not directly used. And maybe a reason for that is that there are like, as far as we know, there are no zone-based algorithms for 180 emptiness check because the decidability result was proved using a region-based algorithm. So we thought of introducing a zone-based emptiness algorithm for 180. So I'll be discussing like highlights of the work we have done, which is firstly, we introduced something called a deactivation operator. I'll try and explain why this is useful and why this can like why this is useful basically. And then I'll try and just touch upon how the zones look and how the zone graph looks for 180. I won't have time to go through with like go over the entailment check, but this is something that is important for the termination of a zone graph in this setting. But yeah, I won't have time for that. But like it exists and we did work on that. And I will also be discussing a subclass for 180 where the zones have good properties. So something that can be like studied further called bounded 180. So okay, firstly deactivation operator. So the example is back again. This is the same automata I went over. This time let's try and look at a run of this automata for this word. So, I mean, it starts with the initial state phi, and then if it reads a point phi and a b, it has like two obligations, like it takes this loop basically, it comes back to phi, and then it resets and goes to true until a, right, and same with b, this is again something, so because of this reset, this loop is taken, so two states are generated here, and then one state from the existing thing is the time elapse, and so on and so forth. The minute C gets read, this obligation dies down because it is within the 1 to 2 that we had. But these two still remain. The minute E gets read, these two also move towards the except like true state. So something to notice here is that this formula is in fact like not dependent on the clock and not dependent on time at all because it's a pure LTL formula. But here, because we have to store the clock value, we are maintaining two states for this, like two states for this one like task to be done, while I mean, it is not necessary. And these two states are basically maintained because of this reset operator. In general, this is required because it is possible for a subclass to have time properties that we need to check. So we need to reset to go towards like a subformula state. But in this specific instant, it's not even required. So what we can do instead is something called a deactivation operator, where we just, instead of resetting the clock to 0, we just say this clock is in fact not required for us in this portion of the automata. So then like we set the clock to board basically. So then kind of it reduces the state. In instances where we know that the clock is not required, we can do this. So this kind of reduces the states that we are using in our runs, and this will eventually, like I'll maybe let you know how this kind of leads towards boundedness in some cases. But yeah, this was the first thing to discuss. Coming to zones, for people familiar with timed automata, zones are conjunction of constraints. Usually they are on clocks. Here we have one clock. So they are on a set of variables. So like if you recall, like these are how the configurations look. So the zones have to like be on variables where each variable has like a state associated with it and an index, because it could have like multiple states could exist in a configuration. So like for example, this is a zone and this is a configuration that lies in the zone. So how the zone graphs look, a rough idea. This is the initial zone, it's a time elapsed zone. And then the successor computation. At each state, we have a formula for the next transition to take, right? Which like the formula can be thought of as a OR of ANDs. So then for each of these like outward transitions, we pick one of the ORs and then we kind of deal with each of the ANDs and like incorporate the like what these are trying to do in the next zone. It is very vague, but I do not have time to go through technicalities, but like the basic picture is this. Right. And then the thing with this is that unlike traditional zones, here the variables, the set of variables could be unbounded. One like dummy example for that is this automata that just has a loop. One is a resetting transition, one is a non-resetting transition, and this will just like keep leading to more and more states added. So then what we introduce next is something called a bounded 180. It is like a restriction on 180. We study these like basically we kind of bound the number of states, number of active states each reachable configuration can have. I say active because it is possible for a configuration to have a lot of states that have the clock to be bought, because it could have been a deactivated clock. The active states are something which we need to actively like store in our zone. So this is something we are interested in. Like having a bound, basically, it gives us a global bound on the variable set of the zone that I mentioned. And these are useful because in a vague sense, if there is a bound on the number of variables, the zones behave like the k-clock automata zones will behave. So one useful subclass of MTL that follows this properties, like the construction I said from MTL to 180, that still satisfies this bounded thing, is one-sided MTL. And yeah, I think my time is running out. So basically the left side of the until formula is a pure LTL formula. In this case, it leads to bounded things. And like, okay, thank you.
Thanks for your talk. So you just said that the zones for bounded 180 behave like automata zones. What is the difference? How do
I mean, I said behave like because I was like being a little vague. So if the zones have a fixed set of variables, um, here there is still a complication because like each like okay, there is an implicit like step happening in the timed automata zones, which is like a mapping between two zones. So anytime you have to compare two zones, you implicitly map the clocks of this zone to the clocks of that zone. In general, the clocks are the same for timed automata.
Right.
So that mapping is something that like exists always, and that is like easy to find. That is like a kind of negligent step. Here, it is still an explicit thing that you have to do because the states need to be matched. Once the states are matched, which is why I said like, because here so if you're familiar with timed automata zones, in order to get termination, there is like a subsumption relation. Like you compare two zones, you say, okay, one is subsumed by the other and you end. Here, the subsumption relation becomes a lot more complicated. Again, because the variables are different.
Okay.
Yeah.
Thank you.
Okay, the next talk.
So Anindam is going to tell us about gray box learning of languages recognizable by event recording automata.
Hello everyone, I am Anirban. So I'll be talking about gray box learning of ERA recognizable languages. So this is a joint work with Sharon, who is probably online, and with Joshua, and this work has been done when I was at ULB Brussels. So what are event recording automata? So these are basically subclass of timed automata, which you have already seen many times in this conference and workshop. So timed automata are basically finite state automata with some clock variables. So here is an example. I'm not sure whether you can see. I think you can see now. So here we have some letters, some variables which are called clocks, and some guards and some resets. So what is special in this class of timed automata is that we have two restrictions. First, for every letter sigma, there is only exactly one clock x sigma. And there is also, so for A there is XA and for B there is XB. And there is another restriction is that on letter sigma you reset X sigma. So basically you only reset XA when you are reading A and you only reset XB when you are reading B. So somehow these resets are fixed, and so from next on we can just forget about these resets, but they are there, so they are implicit. So basically one can think of this kind of order as basically the clock XA is recording the time from the last occurrence of the event A. So that is why it's called event recording. And as usual, this kind of automata accepts timed words of this form. So for example, in this example, the automaton accepts the language A, B, A, B, A, B, A, B of this form such that every B occurs at exactly after one time unit of the previous A, and every A occurs at most one time unit after the last B. So the objective of this work is to learn this kind of automata. What do I mean by that is that given an ERA recognizable language L, we want to learn an ERA that actually recognizes it, and this is in active learning settings. So I'll quickly go through the framework of active learning, since I don't think it has been introduced in this conference or workshop. So in the active learning framework, you have basically two entities. One is learner, who is basically learning a representation of the language L, which is basically with the teacher. So teacher knows the language L. So learner iteratively asks questions to the teacher. So it can ask two kind of queries. One is membership query. So the learner can ask basically whether a word is in the language L or not, and teacher will say yes or no. This is easy. And then learner will do some calculation and come up with a hypothesis and ask the teacher whether this is the language you have. The teacher will either say yes, exactly, or it will give a counterexample saying no. So this is the framework. So one thing is that here we use inclusion queries instead of equivalence queries in these particular works, but rest stay the same. So okay, again, this is the problem statement. So basically we have an ERA recognizable language L, and we want to output a deterministic ERA that accepts exactly the same language. Okay, so one step further, we will output a DERA which has minimal number of states. So this will be done by a reduction from this problem to the regular separability problem. But before going there, let me give you an intuitive example. Okay, let me give you an example. I don't know if it is intuitive or not, but so this was the example from the last slide. AB, where every B is at after one time unit from the last A, and every A is at most one time unit from the last B. So can you draw a DERA which has less number of states? So anyway, So yes, the answer is yes, but it's a bit tricky. So here you see some strange, not strange, but some more elaborated transitions, like guards on the transitions. So what basically happens here is that so you can actually think that this kind of ERA is accepting symbolic words. So you can say, okay, this ERA is accepting this kind of words, where true means basically no guard. So a comma true and b x equals to 1, this basically this guard, and then a x b less than equals to 1 and whole star. You can think of it, you can think of the language of this ERA to be concretizations of words of this form. But when you do this for the other automaton, you will see there is some inconsistency. So what do I mean by that? So if you look at this word, a comma true and a comma this guard, so this can be read in this automaton if you treat it as a DFA. However, this is inconsistent. What do I mean by that is that there is no concrete timed word corresponding to this symbolic word. So basically what is happening is that there are two kinds of symbolic words. One is consistent and one is inconsistent. So for the consistent words, we expect them to behave correctly. That means if it is in the language, then it should be in the DFA language also. And if it is not in the language, then it should not be, like it should be rejected by the DFA also. But for the words which are read, like which are inconsistent, we don't really care whether they are getting accepted or rejected by the DFA. So this, so pictorially you can also think of, so this is, let's say this is the set of all symbolic words. So you can basically split this set into two. One is set of consistent and one is set of inconsistent. Now what is happening is there basically you can further split this box into two, the green and the gray, where the green is basically all set of all symbolic words which are in L. And consistent, like which is in the time language and consistent, and L bar is this. So you want to find a timed automata or a DE array that basically accepts everything in the green and rejects everything in the gray. So it can go little bit further, as I said, because these are set of inconsistent words. So this is exactly the problem of regular separability. Okay, I say regular separability because it turns out that everything in these small boxes are actually regular. And so we use this regular separability algorithm called LSEP by Chen and others, and we use this to learn DE array, and we call that LSEP. So let me give you a overview, like high level idea. So we start. So this is the same box, but we start. We basically learn a model D that accepts some words which are consistent and inside L, so this green ball, and rejects everything in the red gray ball. So the idea is to gradually increase these balls such that this green part eventually becomes the whole L, and this gray part eventually becomes the whole L bar, as you saw in the last slide. And so here you have to use some membership queries and inclusion queries. So here exactly we need inclusion, and that's why we did not want equivalence. And then from there, you would like to come up with a DE array. So here it was not a DE array, here it was something else. But from here you would like to draw a DE array, which is basically consistent with these two balls. So what I mean is that everything in this green part is also getting accepted in my DE array, and everything is which is in the gray part is outside LA. Then I'll ask the teacher whether this is my correct DE array or not. If yes, then good. If not, then the teacher will say, oh, look, this is a counterexample because this is in L, but this is not getting accepted in your automaton. And similarly, the red one, so there is a red dot, if you can see. This is in L bar, but it is in your getting accepted in your language. So then this will be taken care of by the learner. So it will basically include this green dot and include this red dot in the gray part. And this will go on, and it will eventually converge to a DE array. So if you remember the framework of L star, here we are. So this, so here we learn a model D that that accepts some words in L which are consistent and rejects something which are in L bar inconsistent, and from that we constructed D array. So I'll not go through the model D array D, but this somehow looks like a DFA or D array, but here we have three kinds of state. One is accepting, one is rejecting, and one is don't care. So basically, everything that goes to the accepting states is accepted, everything that goes to the rejecting state is get rejected, and don't care, basically I don't care whether, so I don't care about the words that go to the don't care states. So yeah, usual results is that, so we prove that this algorithm terminates, this is correct, and we get an automaton with minimal number of states. So we also implemented this algorithm, but not exactly, with some heuristics. So there are two heuristics, if you remember the picture. So first, we don't consider this intersection with consistent because it is hard, and also we don't consider minimality here because it is NP hard. So we design an algorithm which runs in polynomial time, but minimality is not guaranteed. But empirically, we see that we learn small automata. And so there exist some active learning algorithms for deterministic timed automata, yes. So this was work in 2023 by Masaki Waga in CAV. So we compare with them and we see that membership in terms of membership queries, so this LearnTA is the tool by Waga and TLSAP is ours. So we see that in terms of membership queries, we do better. Yes. So to conclude, we have designed an active learning algorithm of ERA recognizable languages that give a ERA with minimal number of states, and we have an implementation. And these are some extensions which we are looking at. Is that so? Can we extend this methodology for larger classes of like timed automata? Or so here, if you remember, in the two-state automaton, the guards were a bit messy. So can we do with better looking guards? Thank you.
Quick question about the experiments. What was the number of states in the LearnTA?
Yes.
I mean,
So
roughly, yeah.
no, so that is so roughly it is actually quite less because they use some kind of different kind of resets, so they can reset to another clock value.
Okay.
So that is why they get lesser number of states. I think that is why, but yeah, it is also reasonably less.
Okay, thanks. And the number of clocks, is it?
So they have so they reset one clock per transition, I think. Yes. There are a huge number of clocks, yes. But they are generally like deterministic time automation. It's not restricted to ERAs.
I have one question. So this IQ, this is inclusion queries, and this MQ is membership queries, right?
Yes.
So it I mean it is quite low, and because different, is it the reason you are not using membership queries?
No, I am using membership queries. I am not using. We are not using equivalent.
So what about this SMQ and TMQ?
So this is their tool, and they had some symbolic membership queries and timed membership queries. So
okay.
we are not really. I'm not really sure what exactly they are.
Okay.
But yeah, that's why I reported both of them. But I think the most relevant parameter to compare is this with this.
Okay. Okay. Thanks.
So something similar. So in your model, all the membership queries are symbolic queries, is it?
Yes, and so yes, because so we somehow consider regions, and you can we query regions. Yes, yes, they are symbolic.
thanking the speaker.
He's gonna present now, and the title is Partial Observation Recent Computation Results.
Thank you. Super. So some of the topics have appeared during the various talks, so I'm happy. This is many results during my whole PhD and work with many people. So it will be many results, no proofs. Hope you are for the right. So more into computer science, and then we'll go into game theory. Probabilistic finite automata. It's an automaton where each transition has probabilities. So if we start in S1 and we process the letter A, you might go with probability a half up or a half down. Up is the happy state, you terminate. If you go down, what happens? Well, you continue processing letters, right? In case that you process the letter B, then you immediately go, and that's it. So this is an automaton, has probabilistic transitions. Nothing especially new about it. What is the language that it defines? Since there are probabilities, you might accept or not, you might terminate in top or bottom. The language that it defines are the words which are accepted with probability larger than a half. So in the previous example, you accept every word that starts with two A's. Yeah? Because you go to the acceptance state with probability 3/4, at least. And the problem that you want to solve is the emptiness problem. Is there any word at all in this language? Perfect. So the big result for this very simple model is that everything is undecidable. So in the same year, same paper, we say, well, emptiness is undecidable, and even if I promise you that every word is either accepted with probability at least 1 minus epsilon or at most epsilon, there's nothing about close to a half. Just either almost accepted always or almost rejected always. Even under that promise, the problem is undecidable. So very simple model, very hard undecidability. What do we do? Do we look into subclasses? Do we look into the structure of the graphs? I take a different approach. So I work in game theory, workshop on games. Let's see what games can say about this. I'm going to extend slightly the model. Now, there is no automaton. I have players, or one player. There are no letters, there are actions. Right? So you start in some state, and you might take an action win or an action lose. After an action, there will be a probabilistic transition, and there will be information back. So this is new with respect to probabilistic finite automata. The information is a signal. So let's say that So let's say that we start in both states with probability a half, but we don't know in which one. Perfect. Now we are not, we don't want to lose, so we want to win, and we play win. What happens? What do we know that happens? We know that we stay on the same state, whichever it was, and we receive a signal. So if we are in the left state, we receive a signal set plus or set minus with probability half a half. where in the other one, you just get with different probabilities. So after playing win once, you might get an idea that if you get set plus, then you are more like in the left state, and if you got set minus, you're more in the left. If you play win a lot of times, then maybe you do a statistical test and you more or less know where you are. So you learn as you play, and you have probabilistic transitions. Of course, it can be more complicated than that. In this case, if you play lose, you just go and lose. All right. So this is the model. Any questions about the model? No. Great. Okay. There will be many objectives. Reachability is the simplest one. Buki and Kabuki is I want to reach infinitely often or reach only finitely often some states. And I put rewards, sorry, to not indicate it. In this model, probabilistic partially observable Markov chains, every state will be given a reward, a number. So in this case, it's just reachability. Here is 1, here is 0, but you could get rewards along the way. So if you get rewards along the way, you would like to aggregate them, for example, as an average and take the limit or just the limit reward. The limit reward subsumes Buki, Kabuki, and reachability. The limit average reward subsumes only reachability. And in this setting, we're going to ask a bunch of questions. So what are the questions that we can ask? If you're in reachability, maybe simple question, is the value 1 or not? Again, in the probabilistic finite automata world, the answer will be it's undecidable. Many of these questions will be undecidable in the probabilistic finite automata, but we will see some natural restrictions in game theory where you can answer these questions. Can you compute an epsilon optimal strategy? That's a very natural question. Can you approximate the value? Can you, given a model, given a property, and given a model, can you check that this property is satisfied in the partially observable NDP that you're given? Maybe you want to check that it's nice to work with. Is there an algorithmic way to check this property? Okay, so now it comes the wave of results, one for each of these problems. First result. In a probabilistic partially observable MDP, you can decide if qualitative reachability in NP. Oh, wait, it was undecidable, now it's in NP. What happened? Well, over constant memory strategies. Now, constant memory strategies do not make sense in probabilistic finite automata, but they make much more sense here in the game theoretical perspective. How should you think about this result? General strategies are like every word, then it's undecidable. If you consider constant memory strategies, then it is existential theory of reals, and we take down from ETR to NP. Perfect. Second result. The general problem is undecidable, but here it's for the limit average objective, which subsumes reachability. Reachability in a PFA, you might try every word, and you eventually, let's say that if it is empty or not. If it is not empty, you will find a word and say, hey, it's not empty. Now, this limit average objective is harder than reachability, so maybe it's even more undecidable. This result says, no, it's also recursively enumerable. Meaning there exists finite memory epsilon optimal strategy, so if you want to approximate the value, you can check through all finite memory strategies. Okay. A result. In blind NLP, so there is only one signal. This is really the probabilistic finite automaton, but not with reachability objective, with limit average objective. So it subsumes reachability. What can we say? The value approximation is not undecidable anymore. It's second exponential space, doesn't matter. Is decidable. What's the assumption? The assumption is that the transitions are ergodic, meaning that after a very long time, it doesn't matter where you started, you know that you have the same belief no matter where you started. This makes no sense in reachability for probabilistic finite automata, because if you started in the goal state, you are in the goal state, fine. But it makes much more sense in this model. So this is a subclass of all the blind MDPs, which in general are undecidable. In this class, it is decidable. Perfect. There is only one signal. So as a player, you never get any information from the signals. You take an action and you receive the signal, the unique signal. So it's the same as in the probabilistic finite automata.
So in the black box,
Yes. So last two slides. There will be these three actually. Sorry. There will be properties that I want to check of a PMDP. In practice, if you're gonna use a model, it's because it's modeling something in reality and you will like at least some continuity. So it should not depend on the numerical probabilities that you put in the model. For example, if a transition is 0.4 and in reality is 0.40001, you will like that your conclusions do not depend on this number. So what kind of conclusions? Well, these are three properties on the value and on the strategies. What are the results? Well, in the general model of PMDPs, it is undecidable to check if it is value continuous or not. So as a model, even you studied the real situation, you came up with a PMDP, it's great. Your model should be value continuous so that your conclusions convey something about reality, but it is undecidable to check if it is value continuous or not. So you're on your own, there's no algorithm. What's the bright side? The bright side is that if it is a blind MDP, then it is continuous. It is continuous on the values, it is continuous on the strategies. And the surprising thing is that it's even more continuous than the classic model of fully observable Markov decision processes. The property here is a strong strategy continuous. We can talk about it later. Thank you. Yes. So in the weak strategy continuity, what I ask is, think that you have your model and you have another model which is close. So two PMDPs.
okay, I think I can see. Okay.
Yeah. They should have some epsilon optimal strategy which is in common.
Thanks.
Any questions?